Good morning everyone. I am here to record a lecture based on PN junction, and it is in continuation with the last lecture that is based on intrinsic, extrinsic semiconductors and all. So in this lecture we are going to see how the PN junction will work. So we already know that how P and N type of semiconductors will be created. So if you want to create a P type of semiconductor, you have to add a acceptor type of impurity into the proper pure form of silicon crystal. And if you want to create a N type of semiconductor, then you have to implant, or you have to give the impurity which is donor type of impurity into the semiconductors. So here we can see that the condition when there is a combination of P type layer and N type layer, then it results the formation of the PN junction. So we have two layers, that is P type layer or N type layer. As I have told you that P type semiconductor is only when there is acceptor type of impurity is there. So P type, for P type we have acceptor type of impurity, and for N type, for creation of N type of semiconductor, we want donor type of impurity. So in the earlier lectures we have already discussed that what are donor and what are acceptor type impurities. So for donor type impurities like phosphorus we can use, and for acceptor type we can use boron or aluminium. So these type of impurities which we can add into the pure form of the silicon crystal, and they will create a P type of semiconductor material or a N type of semiconductor material. So in this figure we have N type of layer and P type of layer, and in between there is a depletion layer. So we have P type of semiconductors and N type semiconductor, and in between there is a depletion layer. So in the last lecture we have already discussed about the lasers phenomena. So in the lasers phenomena we have same type of structure is there, that is P type or N type semiconductor, but in between there is an active region. So which is basically, the lasers are basically made up of semiconductor devices. So active region is there in between the P type of N or N type of semiconductors. So we provide here positive voltage to P type and negative voltage to N type, and you can see that when you provide positive to P type and negative to N type, the holes in the P type will repel from the positive side, and the electrons in the N side will repel from the negative side, and they will cross the junction, and they will the immobile charge carriers will be deposited in the depletion layer, and we have a thin depletion layer in the case of the in this situation, and it is called as forward biasing. So when we provide positive voltage to P type and negative to N type, it will give you forward biasing, and when we provide negative to P type and positive to N type, it will give you negative to P type and positive to N side, then it will give you reverse biasing. So we will see later on that how the characteristics of PN junction will come whenever there is a forward biasing and whenever there is a reverse biasing. So junction is basically is defined as the point of contact of the two semiconductors layer. In case of lasers, we call it the junction is called as active region, or the depletion layer is called as active region, where the electron and hole pair will be generate or recombine. So in the last lecture we have seen that how the electron hole pair generated or recombination will occur. So whenever there is recombination of the electron hole pair, then there will be emission of light, and when there will be generation of electron and hole pair, there is formation of the electrical charges, or electricity will flow there. So in next slide we have the diode. So we have the same thing, that the N type and P type semiconductors, and majority carriers in the N type side is electrons, and majority carriers in the P side is holes. So in the depletion region we have, from the N side, we know that whenever there is a positive supply to P side and negative supply to N side, they will cross each other, the carriers will cross each other at the junction, and we have immobile charge carriers at the N side, that is positive holes, and at the P side junction we have negative electrons. So for a diode, n-type region has majority charge carriers as electron, and there are minority charge carriers as holes. And for a diode, p-type region has majority charge carriers as holes and minority charge carriers as electrons. So this will give you the all view of the how the majority charge carriers and minority charge carriers are in the case of the p-type and n-type semiconductors. So next we have PN junction diode with no bias, when we are not providing any bias. So this is the condition which I am talking about, when there is no biasing, but when you provide bias, there will be forward biasing or reverse biasing will occur. So biasing is defined as the process of applying voltage across the diode. So when you apply any voltage across the diode, across the like a PN diode, we will call that as biasing. So the condition when no voltage is applied across the diode is called as no biasing condition. So whenever you are not providing any voltage to a particular diode, it is called as no biasing. So in this case, there is no movement of charge carriers because you are not providing any kind of bias. So there is no movement of charge carriers, and hence potential barrier remains unchanged. So there will be no change in the potential barrier. So what is potential barrier? Is as this is the depletion region. So potential barrier is basically how the electron and hole are crossing at the junction and how much energy they required, the potential they required for crossing it is called as potential barrier. So built-in potential in the case of when there is biasing or is 0.3 to 0.7 volt. If you are not providing any biasing, then there will be no change in the potential barrier. The potential barrier remains constant and there will be no flow of charge carriers across the junction. So this is the condition when there is no biasing. So what we have, we studied here that biasing is defined as the process of applying voltage across the diode. The condition when there is no voltage is applied across a diode is called as no biasing condition, and in this case there is no movement of charge carriers and hence there will be no flow of charge carriers, no flow of current is there, and the potential barrier remains unchanged. So in this figure we have N type of region, we have P type of region. In N type of region we have electrons, majority carriers, and in P type of regions we have holes, majority carriers. The depletion region has negative charge carriers at the N side and the positive charge carriers at the P side when there is no biasing. When we provide biasing, there will be a flow of the transition of the electrons and holes from this side to this side, or from electrons from left to right, and for holes from right to left. So there will be a change in the minority charge carriers in the across the depletion region also, and there will be a change, obviously there will be a change in the built-in potential or the potential. So in the next figure we have the zero biasing condition. We are not providing any voltage here. The resistance is given as R and the diode is given as PN, which has a positive and negative this side, and we are providing ground and there is no biasing. So obviously there is no flow of charge or the electrons and holes across the junction. So the built-in potential will remain constant, that is 0.3 to 0.7 volt, which is for silicon it is around 0.3 and for germanium it is around 0.7. So we have the same built-in potential will be maintained throughout the junction. So what is PN junction with forward biasing and reverse biasing? So when you are applying any voltage, how the electrons and hole movement will change, okay? So right, so in a reverse biasing mode, the N terminal is connected to positive of the battery. We already know, we have discussed this. So in the reverse biased mode, the N terminal is connected to positive of battery and the P terminal is connected to negative of the battery, due to which what will happen if you are providing positive terminal, positive side of the battery to N type of terminal and negative side of the battery to P type of terminal, the electrons and holes get attracted to their opposites terminals. So the electrons will get attracted to the N type, P type of positive terminal of the battery, and the holes will attracted to the negative terminal of the battery, and the depletion region will become wider here. So you can see from here that the depletion region becomes wider because of this, because electrons will move from this side, because we are providing positive side to this and negative side to here, negative terminal to here in the P region. So electrons will get attracted to positive side and holes will attracted to negative side, and they will get separated from each other, or they will not cross the junction. So the depletion layer will get wider and wider, and there is no flow of current. So in this case, there is no flow of current, or minority flow, or negligible amount of flow of current, you can say negligible amount of flow of current. So which very less current flows across the, because very less means very lesser amount of the current flows across the diode, and it is non-conducting mode, and also the potential barrier goes up. So here the potential barrier will again goes up to certain level. In forward biased mode, what will happen? In forward biased mode, the N terminal is connected to negative battery and the P terminal is connected to positive of the battery, due to which very large amount of current flows across the diode, and it is in conducting mode. Also the potential barrier goes down. So in the case of the forward bias, which is very useful for getting very less or thin depletion region, or the electrons and holes will get crossed to each other at the junction, and we have a very high amount of current will flow inside the PN junction. So these two diagrams depicts about how the reverse biasing of a PN junction diode will work and how the forward biasing of the PN junction diode will work. So in this case, you are seeing in the from the diagram also that the N region has number of electrons, majority number of electrons, and the P region has majority number of holes. So what will happen when you provide negative to N side and positive to P side? The negative electrons will get attracted to positive terminal of the battery, and the positive holes will get attracted to negative terminal of the battery, and they will cross the junction. So very small depletion region is layer is there. So in case of reverse biasing, the depletion layer is wider, but in case of forward biasing, the depletion layer is smaller. Okay. So next what we have, the PN junction diode characteristics, which is very important, because we have to see what is the characteristic of the PN junction diode, how the current will goes on increasing as versus voltage. So the ideal diode characteristic define the graph parallel to current axis, which means that diode will be on in forward biased mode and it will be off in reverse biased mode. So this is the important point. The diode will be you can say the diode is in short circuit mode in the forward biased mode, and it is on open circuit mode in the reverse biased mode. So the characteristics are somewhat that as you increase the voltage, the current will keeps on increasing. So and in the reverse direction, it has a reverse current, or the as versus to the voltage, and there is some leakage current. In practical characteristic of diode, what will be there? In practical characteristic of diode, in forward biased mode, current start rising slowly or initially. So it's rise initially very slowly at a particular cutoff value, because if we are taking suppose silicon or germanium, it has a some cutoff value that is 0.7. So at a 0.7 volt, it keeps on increasing. It goes increased instantly. Okay. So in practical characteristic of diode, in forward biased mode, current starts rising slowly initially, and then it rises later on, while in reverse biased mode, the current initially is very minimum, and as the reverse voltage increases, then the junction breaks down and current rises abruptly. So there is two types of leakage current here. One is leakage current and one is avalanche current. It is also called as avalanche breakdown. So at a particular value of the voltage, it gets breakdown, or you can say that diode will get breakdown, or avalanche breakdown is there, and there will be a highly increase of the current in the negative direction. So this graph basically shows the current in the negative direction, which is basically you can say that it is dipping, or the current in the positive direction will keeps on increasing after a particular voltage, that is 0.7 volt. So this will show about the diagram, these two diagrams will show about the characteristic of the PN junction diode, how it will work in the reverse biased, how it will work in the forward biased. So you can see from the below figure also, in the forward biased case, we have the current flow from positive to negative terminal, and we have a short circuit here. This is the short circuit. Short circuit is there, and here I naught is greater than 0 and V naught is equivalent to 0. In the reversed bias case, we have open circuit. Diode is open circuit, and the current will be here 0, and we have I naught is equivalent to 0 and V naught is very much less than 0 here. So next we have potential barrier. So as we discussed that how the forward biased and how the reverse biased characteristic is there, and what is the role of the potential barrier is there, because if the potential barrier is very high, the electrons and hole movement from one side of the terminal of the diode to other side of the terminal will get hampered. So we have to see that how to reduce the potential barrier so that there will be a proper transition of electrons and holes across the junction. So the electrons in the N region have to climb the potential hill. Obviously, it is called as, because it is called as potential barrier, they have to climb a particular voltage value so that they will reach the P region. So the electrons in the N region have to climb the potential hill in order to reach the P region. Electrons trying to cross from the N region to P region experience a retarding field of the battery, and therefore they get repelled. Similarly, for holes is there from the P region. So potential thus produced are called as potential barrier. For the germanium it is 0.3 and for the silicon it is around 0.7 volt. So we have this type of potential barrier, for these values of potential barrier for the silicon and germanium side. So what we are seeing here, that how the potential barrier is keeps on increasing in the case of the reversed bias, but in the case of the forward biased it has a very less, it will keeps on decreasing, and that will help the electron and hole to move properly across the junction. So for this we have to see that what is the earlier potential or what is the earlier potential barrier, and if we are providing a forward biasing, how the potential barrier keeps on decreasing. So you can do this in experiments also in the lab. You have to see, you can draw the characteristic of the PN junction. You can do the one experiment on this PN junction, and you will see just that at a 0.7 volt for silicon, if you are using silicon diode, 0.7 volt of silicon, there is a abrupt change in the or rise in the current at a particular at this voltage, that is 0.7 volt if you are using silicon. But if you are using germanium, it has a potential cutoff value of the voltage is around 0.3 volt. So the germanium is best suited because it has a lower, you can say lower cutoff voltage as compared to silicon. So there are some formulas which we can use for the PN junction built-in potential. PN junction built-in potential can be referred as V built-in, and it is equivalent to KT by Q ln Nd Na by Ni square, where Nd is the your donor concentration and Na is the acceptor concentration. Ni is the intrinsic. We have already discussed these terms in the earlier slides where I have talked about intrinsic and extrinsic semiconductors. Intrinsic semiconductor concentration. So we have this, that the KT by Q, which is KT by Q is equivalent to around, in numerical problems you can take 0.026 volts. So 0.026 volts we can take in the numerical problems. So KT by Q ln Nd Na by Ni square, which is the built-in potential. So V built-in is built-in potential in volts, Nd is n-type donor atoms concentration, Na is p-type acceptor atom concentration, small n is the concentration of the electrons, and which you can call as Ni for the Ni square if it is electrons, n, or if it is for holes it is p square. So KT by Q is the thermal voltage, T is the temperature in Kelvin, which is 300 absolute value, and Q is the charges in the coulombs. So this is a formula for getting the value of the PN junction built-in potential. So by putting the values of Nd or Na, suppose we have given Nd that is 10 to the power 17 per centimeter cube, which is the donor concentration. Na acceptor type concentration, that is 2 into 10 to the power 15 per centimeter cube, and Ni suppose given it is 1.8 into 10 to the power 6 per centimeter cube. By putting the values of Kt by Q, Ln, Nd, Na upon Ni square, we can find out the value of V built-in potential easily. So by having these values, putting these values into this equation, this will V built-in potential equation, you can get easily the value of the V built-in, and this will give you idea about how the built-in potential, how much is the built-in potential and how much the data is to be required, how much is the voltage level to be required to be minimized or extended for getting the electrons and holes to move from one junction to one part of the p-n junction diode to other part of the p-n junction diode. So next is the depletion region width. So equation for width of the depletion region in open circuit when there is no voltage applied here. So for open voltage, when there is open circuit, when there is no voltage applied, is W is equivalent to 2 under root 2 epsilon by Q 1 upon Na plus 1 upon Nd VBI, which is V built-in potential. So here epsilon is the permittivity in farad per meter. Epsilon naught is equivalent to epsilon naught epsilon R, where epsilon naught is the permittivity in free space and epsilon R is the permittivity in the medium. So epsilon naught value is the 8.85 into 10 to the power minus 12 farad per meter. You can put in for getting the expression for W, and epsilon R is relative permittivity of medium or dielectric constant of the material. So here we have epsilon R value is 11.7 for silicon. In general numericals we put this, and epsilon R value is 16 for germanium. So by having these values and with this equation you can find out the potential depletion layer width. So this is depletion layer width. So these all equations will come, you can solve it in numerical problems. You have to put these equations. So here Q is a charge which is normally 1.6 into 10 to the power minus 19, and VBI is the built-in potential. VBI is the built-in potential. So we can see how the depletion region width will vary for the case of different cases of the built-in potential. So whenever built-in potential is very high, depletion layer is very high because it is directly proportional. So W is directly proportional to VBI. So here as you increase VBI, as you increase, W is also goes on increasing, and whenever VBI decrease, in the case of, this is the case for the reverse biasing and the forward biasing, the case when VBI is very less and W width of the depletion region is also very less. So we have this type of depletion region width in the case of the semiconductors. So next is the diode characteristic equation, which or it is also called as Williams-Shockley equation of the diode. So we have diode equation which is ID is equivalent to Is e to the power Vd upon eta Vt minus 1. ID is the diode current, Is is the reverse saturation current here, Vd is the forward bias voltage across diode, eta is the ideality factor which is 1 or 2 depending on the various factors, Vt is the thermal voltage, Vt is equivalent to Kt by Q, K is the Boltzmann constant, that is around 1.38 into 10 to the power minus 23. T is the absolute temperature in Kelvin, which is again 300 Kelvin. Q is the charge of the electron, which is 1.6 into 10 to the power minus 19 Coulomb. At room temperature we have, that is at 27 degrees Celsius or 300 Kelvin, we have Vt is equivalent to 26 millivolt, or you can say Vt which is Kt by Q, which is equivalent to 0.026 volts. So this equation, diode-Shockley's equation, you can see from the figure here, that is we have a characteristic curve between V0 and I0, which is in milliampere, and here the breakdown voltage or the reverse bias current is very less, that is in microampere. So as you increase the voltage, there will be a change in the current also, but at a particular cut on knee voltage, for that we have, for silicon it is 0.7. So here it is 0.7 for silicon. We have a drastic change in the current. On the other hand, in the reverse bias we have the as you increase the voltage, the current will keeps on dipping on at a negative level. So we have very less current in the case of the reverse bias. So in the forward biased we have the current in milliampere, but in the reverse bias we have the current in the microampere range. So this give you an idea about the Shockley equation, give you an idea about what is the diode current, whatever, when you are providing forward biasing, what is the value of the current it is flowing inside the diode, in the diode. So ID is equivalent to Is e to the power Vd upon eta Vt minus 1 will give you the overall diode current. So next, in the next lecture, what we are getting about that how these diode equations will work, and how the parameters of the electrons and holes, and how the p-n junction will be useful in having these equations. So as we have already done in the last lectures, that how the recombination of electron and hole pair will comes into picture, and how the lasers will work. As we already discussed about how the lasers have a theory of Einstein, and they will follow both the simulated and stimulated, spontaneous and stimulated emission. So in the next lecture we are going to see how these lasers will work, how these factors, that is like a diode saturations current or the Shockley equations, will give you an idea about the current flow in the laser, or the current flow in the detector, you can say, in the receiver part. So in the next lecture we are going to see all these things. Thank you so much.